Hello everyone. In today's session, we are going to discuss about Turing machine. I'll take one problem and I'll show you the different ways in which we can represent a Turing machine. Okay, different ways in which a Turing machine can be represented. One simple example, I'll show you how to construct a Turing machine for it. Okay, so you know what is Turing machine, right? Turing machine is a mathematical model and that is going to have an infinite tape as a memory unit. Okay, a tape with infinite length and this tape is split into cells. So you will have a lot of cells in between. Cell is actually meant to be a small space and you have a read-write head focusing on the first cell. So each cell is capable of storing one alphabet at a time. So if I take my input as an A-B combination, one cell I can write either A or B, one alphabet at a time. And similarly, if my input is of a binary element, I can write either 0 or 1 in each and every space. Okay, so now this is the usual constraint and we start with the starting state of Q0. And when can we call a Turing machine is, when can, like language acceptance of a Turing machine, when can we say that the input is accepted by Turing machine or not? So whenever a Turing machine enter into an accepting state, the input is accepted. And whenever it enter into a rejection state, the input is rejected. Okay, so we have a special acceptance state over here and whenever a Turing machine enter into it, we say that the input is accepted. Okay, so this is the constraint. We are not going to go end of your input like your NFA, DFA or a PDA. Okay, what happened with NFA, DFA, push down automata? We just go start from the starting alphabet of the input till the end of the input and after reaching the end of the input, we say that the input is accepted or not. Over here in case of a Turing machine, whenever this transition state enter into a accepting state, the input is accepted. I'll show you an example for it. Let us consider this language. Over the alphabet A comma B. So my input consists of all the combination of A and B and whenever input start with ABB, I have to accept it. Okay, if the initial elements are A, B, B, we are going to accept the input. And it is like programming here. See, all these, whatever we are going to construct over here, it is similar to a C program or a C++ or Java program. So, logic may vary from person to person and the way in which they write a coding or a logical values for it, it differs. Okay, I am not going to say that whatever I am going to write here is going to be the standard one. You can logically think about it and write it in a different pattern too. Okay, so one such a way is my input should start with ABB. This is a very simple procedure. I can just have the input in my tape. See, I told you now, like whenever we start the Turing machine, you have to take this input. If my input is ABBA, this is my input. Whenever a Turing machine is started, this input is written in the tape as ABBA, one alphabet in a cell and followed by the blank representation. We have used Z0 to represent the bottom element of starting push down automata, right? Similarly, to represent the blank symbols, we use this symbol. Either we use this blank representation or we use this hyphen as a representation. Okay, it is up to the user to decide on. I use the capital letter B to denote that this is the last empty spaces. Okay, and the transition will be in the starting state Q0 representing the first element. This is read-write head. It is able to look into the place of the cell and read what content is there and it has the possibility of erasing it and writing it a new content into it. If needed, you can do it. Okay, so my case is the input should start with ABB. So whenever input start with ABB, we are going to accept the input. So one way I can start is in Q0. If my input first element is A, it is in proper structure. I check the next element. Okay, so I can draw the transition diagram like this. So we have a Q0, a starting state. Starting state focus on the first element. If my first element is A, it is in proper structure. I make a move to Q1 state. I am not replacing anything over here. The tape will remain as it is. We don't want to replace it. So A will remain as it is. I make a move to the next element. So next element should be B, right? So if the next element is B, I make a transition like what we have done for your NFA or DFA, the same structure. First element should be A. Got it? And next element should be B. So B, move right. And the next element should be B. If the next element is also B, we are going for acceptance state. We are going to accept the input. I told you now the input should start with A, B, B. Then we are going to accept the input. Now clearly for Q0, read the first element. If it is A, make a transition to the next state. Move right. So the read write head will move from this place to this place. I'll draw the tape structure. So first element is A, B, B, A. The tape remains as it is. If the first element is A, I make a right side move to Q1 state. And what is the next step? Next step is in Q1, if the input is B, the B remains as it is. I just make one step right to the state Q2. Okay, so Q0 when the input is A, I make a transition to Q1. And Q1 when the input is B, I make a transition to Q2. And Q2 when the input is B, the input starts with ABB. It is in proper order. So we can go for an acceptance criteria over here. So the last step here is I can draw a transition like this. A, B, B, A, B, B. I can move right. Okay, since I have written the transition, once we are going for an acceptance state, we can either move right or left, it doesn't matter. So since I have written it as an right side move, I am writing a transition like this. So Q2 when the input is B, we are going for Q acceptance state. And whenever your transition enters into Q acceptance state, your Turing machine stops. Okay, so this is the transition tape structure and this is your transition diagram. And we exactly here know that when your input will be rejected, the input should exactly start with ABB. If it is not starting with ABB, we can have a rejection state too. See here, I can write Q reject here. And when I exactly know that if the input first element is B instead of A, I can reject the input. Or if my next element is in Q1, I want a B, but instead of a B, if I have a I can reject it. And similarly in Q2, I need a B, right? Input should start with A, B, B. If it is not B, you have a here, then we can go for a Q rejection state. So rejection is also allowed over here, a special rejection state where whenever you know that the input is going to be rejected, we are going to trace it over here. Okay, so this is a complete representation of a Turing machine when the input is of the combination of A and B. And see here we haven't checked the last element. We haven't reached the end of the input. We just check first three elements. If the first three element is A, B, B, we are going to accept it. That is the difference between a Turing machine and your other mathematical models. Other mathematical models have to wait for acceptance till we reach end of the input. But we don't care about it. Whatever is needed, we just scan that, and if it is existing, we just process it. Okay. So now this representation we call it as transition diagram. Transition diagram, and this way of representation is called tape representation. Tape representation is something like it denotes step by step how your tape structure looks like. Okay, and there is one more thing called instantaneous description, like you had it for NFA, DFA and push-down automata. So instantaneous description is something at the instant how your input, how your process looks like. Okay, so you have a state and you have a tape structure and you have a read-write head. So we have to write all those things together. We have to merge all those things together. So wherever you have this state, you have to, the prefix of it, you have to add it. Okay, so here the instantaneous description is, I have a read-write head focusing on the first element. So prior to that, I can write it as Q0 followed by the tape element A, B, B, A, blank, blank. See, Q0 followed by A, B, B, A, blank, blank. So this is the instant of my first tape structure. Writing in a one single line is called instantaneous description. So what will be the instantaneous description for this? I can write your A is different. We can write A, and on the prefix of your B, I have my read-write head here, right? I can write the state over here. So Q1 followed by the remaining tape element. This is the instantaneous description structure like this. And over here, I have my read-write head in this place. So prefix to that, I have to add the state. So I can have AB, Q2, BA, blank, blank representation. And the last one, I have my read-write head here in this place. So it is A, B, B, Q except of A blank blank. Okay, so this is your tape representation and this is your instantaneous description. And remember one more thing, when you are writing an instantaneous description, from this step, this is your next step, right? So you can write this symbol. This is called move of a Turing machine, one single move. From this step, I got this step. BBA blank blank. From this step, I got this step. So it is ABQ2 BA blank blank. And from this step, I got the last step as ABB Q except of A blank blank. So this is called instantaneous description. ID description, writing it over here in the structure. So we saw what is a tape representation, what is instantaneous description, and what is the transition diagram. And you have one more specific representation, so two more specific representation when it comes to a Turing machine. So one is called the transition table. So you remember what is a transition table? A transition table is something, you have it like this. We have done it for a transition table for your NFA, DFA, but we haven't done for push-down automata. Okay, the reason is, see, in your transition table, in one side we have all the states. Your states here are Q0, Q1, Q2, Q accept and Q reject state. Okay, and your transition is based on, each step your transition is based on the element that is written on the tape. Okay, so you can write the tape elements over here. Here my inputs are going to be A and B. The element that is written in the tape is also A and B. So for A and B, I am going to write the transition. All the states on the element that is there in the tape, you are going to write the transition. One example is Q0, when the input is A, it goes to Q1 with A as it is. Okay, so it has the A in the tape as it is and make a right side move, making a transition to Q1 state. So this is how you have to write the transition. Okay, so the transition has to be written like Q0 when the input is A remains as it is, move right to Q1 state. And Q0 when the input is B, Q0 when the input is B, it goes to Q reject state and B remains as it is and move right. Okay, a complete description has to be given. So Q1 when the input is A, it is rejected, Q reject, A move right. Q1 when the input is B, it goes to Q2 state. So Q2, B remain as it is, move right. Okay, and similarly for Q2 when the input is A, it goes to Q reject state, and Q2 when the input is B, it goes to Q accept state. Q accept and B remain as it is, move right. And for Q acceptance, you don't have any transition. Q rejection also, you don't have any transition. Okay, so this is your transition table representation. Okay, so transition table representation is something you have to put up in a table structure. So this transition table is applicable only for NFA, DFA and the Turing machine. We cannot apply this in your push-down automata, since the transition in push-down automata is based on the state, input and the element that is there in the tape. So it is three-dimensional thing that cannot be represented in a two-dimensional transition table. So in Turing machine, the transition is really based on the current state and the element that is written in the tape. So we can write it like this. Okay. So now the last representation, a very important representation, is called a formal way tuple rotation. How formally you are going to represent your Turing machine. So you have this, right? Q sigma transition, the element that can be written in the tape. Q0 the starting state and F is your final state. And over F you have two possibilities. You have Q acceptance and Q rejection state. So these are all the tuple notation for a Turing machine. Q is finite set of states. For this example, it is Q0, Q1, Q2, Q accept and Q reject. And sigma is the input elements. Your input is based on A and B. So sigma is A and B. Del is the transition function. You can write your transition function like this. Transition of Q0, when the input is A, it makes a transition to Q1 state by replacing A by A and making the right side move. Okay, so this is one single step of transitions. So Q naught on the element that is there on the tape, it make a move to the next state by replacing A with something. Okay, if you want to replace, you can replace. Here I don't want replacement. So A remains as it is and we are making a right side move. So all this transition that we have taken over here, right, that can be put up in a structure like this. And this term is the transition function. See here, I forget to write, you have a blank symbol representation too. When you are writing a transition table, over the tape element consists of input A and B followed by the blank symbols. So these symbols are also there in the tape, right? So you have to write the transition for that also. Since here it is all null, I haven't noted it down, but make sure you are writing it. Okay, so here the element that can be written in the tape is input element along with the blank representation. And Q naught is my starting state, Q accept state, and I have a special rejection state as Q rejection state. Okay, so this is a complete Turing machine representation for one example that I have taken. So what are the representation we have? Transition diagram, transition table, tuple notation, tape representation for showing your input is correct or not, to simulating an input, and you have this instantaneous description. Okay, so the example that I have taken is very simple. I'll take one more example and I'll show you how it is exactly working for all the representation. So let us take one example where my input is going to end with something. Okay, we know how to construct a Turing machine when it starts with something. Now instead of starting with AB, I'm going to accept all the input if it end with AB. Okay, so I'm going to construct a Turing machine. Whenever my input end with AB, I have to accept it. Okay, so this is very simple, but you have to write the transition over here. If my input W consists of ABB, AB. Okay, if this is my input, my ending should be AB. That is the constraint. Okay, so how can you decide it? Whenever you start the transition, the input is written in the tape from left to right with all this element, one element at a time in a cell, and it is followed by all the blank representation. And my read write head focus on the first element and it focus on the starting input element. Okay, so this instant is going to be same for all. Your input, whatever it is written in the tape from left to right followed by the blank symbol. Your read write head focus on the first element of the cell, that will be the same. Okay, there is no change in that. Now how you are going to proceed it? Okay, my input should end with AB. So you can do it on any way, like you have constructed your NFA DFA for the same case. So like the language that I have taken is a regular language. So I am able to construct NFA DFA or like a finite automata or even a Postron automata or even a Turing machine. See, your language representation goes like this based on your Chomsky hierarchy. So whenever a language is regular or a context free or a context sensitive or an unrestricted language, we can construct a Turing machine for it. It covers up everything. So whatever the problem that we have discussed so far, we can construct a Turing machine. That's why I told you, whenever a language is solvable, okay, whenever a problem you say that it is solvable by a computer, then we can create a Turing machine for it. Okay, a Turing machine is a common representation for all this. Okay, so coming to this problem, I can do any way, like your finite automata or something. One simple way is I can put a loop to reach my blank symbol and I can just move one step left to check the last two elements. Okay, so how can you do it? I can draw a transition diagram like this. I can have a state of Q naught, the starting state, where I just read each and every input until I reach a blank symbol. So I put a loop when the input is A or when the input is B, I keep on moving until reach the blank symbol. And once I reach the blank symbol, I am going to make one step prior to it, a left side move, making a transition to Q2 state. Okay, from here on the thing is easy, right? When I reach the last element blank, and I am going to check what is there in the left side of it. One step prior, if the input is B, the input should end with AB, right? If the last element is B, it is in proper structure. I am going to make one more left side move to Q3 and here I am going to check if the element is A. If the input is A, we are going for a Q acceptance state. Okay. So the same case as the previous one, but rather than checking the first two elements, I am going to check the last two elements. So when I am checking the last two elements, reach till the blank symbol, go one step left. If the input is B, make a transition to Q3. In Q3, if the input is A, you are going for an acceptance state. You can move left or right, that doesn't matter once you are reaching your acceptance state. And what will be your rejection state? Your Q rejection state will be in Q2, instead of B, if I have an A, rejected. In Q3, instead of A, have a B, rejected. Either move left or right, that doesn't matter. Okay. So I think we got a transition diagram for it. Very good. And we have to give a tape structure. So tape structure, I can merge 2-3 things together. Okay. So instead of finding a transition all the places, this is my input. Right. So I am going to, in Q0, I am going to take one step ahead, reading each and every input until I reach a blank symbol. So I combine all the steps together rather than just having a transition to Q0 here, Q0 here, Q0 here, Q0 here and Q0 here. Your tape is going to be the same and your transition is also going to be the same. So I just mix 2-3 steps together. I write it like this. I read all the input, reach the blank symbol. So once I reach the blank symbol, what I did? I move one step prior to my input. So I just move this step to Q2. I haven't written Q1 state. It's okay, fine. I move to Q2 step. In Q2, if the input is B, if the last element is B, it is in correct structure. So I am making a transition to Q3 state. Okay, so I can just draw a transition like this. Table. In Q2, the input is B. I just make one step left and go to Q3 state. In Q3, if my input is A, it is in correct structure, go to an accepting state. So here I can just draw the final structure like this. The entire tape, A, B, B, A, B, blank, blank. And my Q3 focus on this step, right? Q accept. One step left and we are going for an acceptance state. Okay. So this is your tape structure or tape transition. And what will be your final instantaneous description for it? Instantaneous description is, so here I have Q0. So I can write it as Q0 AB, a blank symbol. And here I have reached final. I have clubbed a lot of steps together. So I cannot write one single move. When I write it like this is a single move of a Turing machine. But here I have merged a lot of steps together. In Q0, when I input is A, it moves to right side. And in Q0, if the input is B, move one step right. So I have merged a lot of steps together to reach this place. Okay, so this place transition is blank, blank. So here my tape also remain as it is. Transition also remain as it is, but I merged a lot of steps together, so I can use an asterisk symbol. So what is the meaning of this asterisk symbol here? Asterisk denotes it is a clean closure. With 0 or more move, I am taking from this step to this step. From this step on, with the multiple possible moves, 0 or more moves, I am able to reach this step. Okay, so you can write it like this. And this is the instantaneous description for this. And for this, the instantaneous description is A, B, B, A, Q2, B. You have the blank representation. And from this, I am able to do this. It is A, B, B, Q3, A, B, blank, blank. And from this, I got the last step. So, last step transition is A, B. I have Q acceptance state here, followed by the remaining tape element as B, A, B, blank, blank representation. Okay, so this is my final instantaneous description. So this is called instantaneous description. Got it? And I have pending elements. I cannot complete it in the entire thing, I think, over here. So I will try. So tuple representation is, you have Q, set of Q's here is, what are the states we have? Q0, Q2, Q3, Q accept and Q reject. A finite set of states, and your inputs are made up of A and B, and the element that can be written in my tape is, what are the element that can be written in my tape here? A or B or blank symbol. Okay, and del is your transition function. You can write your transition function for anything. Q naught when the input is A. You have to write everything. I'm just writing one sample. Move right. Okay, del is the transition function. Q naught is your starting state. Q accept and Q reject state are there. So this is your tuple representation. Okay, so what all we have discussed so far? A transition diagram, a tape representation, instantaneous description, tuple notation, and what is left out? To draw a transition table. What all states you have? Q naught is the starting state. You have Q2, Q3, Q accept as the final state, and Q reject. Okay, and your tape symbols are A, B, and blank representation. When you fill it, your table is complete. So Q naught when the input is A, we remain in Q naught state itself. A remain as it is, move right. Q naught when the input is B, we remain in Q naught itself. B remain as it is, we just move one step right. And Q naught when the input is blank, blank remain as it is. We make a transition to Q2 state, blank remain as it is, and we just move one step left. Okay, so you have to complete it. Q2 when the input is A, it goes to Q rejection state. Q rejection, A comma left. Q2 when the input is B, it goes to Q3 state, B remains as it is, move left. And Q2 when the input is blank, you don't have any transition. So Q3 when the input is A, it goes to Q accept state, and A remain as it is, move left. Okay, and Q3 when the input is blank B, it goes to Q reject state, B remain as it is, move left, and there is no transition for all this. This is your transition table representation. So sometimes you will be given with a transition table. Once you are given with a transition table, convert it into a transition diagram for your clear understandability. Okay, then you can proceed on the language that accepted by this. Okay, so I think it gives a complete introduction about what is Turing machine, what all the possible structures, representation that we have a Turing machine. Okay, thank you.